Assalamualaikum and very good morning class. Our lecture today is on exponential Fourier series part 2. Let us move to second example. Example 7.4 triangular pulse train. Find the exponential Fourier coefficients of a periodic triangular pulse train with period t and pulse width tau. The pulse is given as xt equal 1 plus 2t over tau for t minus tau over 2 to 0 and 1 minus 2t over tau for t from 0 to tau over 2 and equal to 0 elsewhere. And the figure for triangular pulse train is as shown in the slide. Okay, let us start solve the problem. First, we put the general equation for xn. And in this triangular pulse train, we have two parts. One from minus tau over 2 to 0, and another one is from 0 to positive tau over 2. And we notice here that xt will be different. And we have to do integration by parts where we have u and integral dv as shown in the red box. So we're going to have two different u. One will be 1 plus 2t over tau and another one will be 1 minus 2 over t over tau. So notice the du, the difference will be in terms of sign positive and negative. The solution will be long, so before that let us keep the du and u, dv and v. So we put one by one. So in this slide I put red color for u times v and the black color is for integral u dv. So the first part plus the second part. First one, the integral is from minus tau over 2 to 0, and the second one will be from 0 to tau over 2. So let us solve the equations. So this is the first part, and notice here that the red one is for the uv, and I substitute the t. For the first one, the t is 0. And the second part is the t is minus tau over 2. And the black color is for integral of v du. And we have three constant variables here. So 1 over minus j2 n pi times 2 over tau and t over minus j2 pi n. And then times the exponential with t0 and t minus tau over 2. And the next one is the second part of the pulse. So the red one again is the uv and the black one is the integral v du. So this time the limit will be t first and then 0, tau over 2, sorry, and then the second one also tau over 2 minus 0. And if we put it everything here, so I show you the equations, the red one and the black one, the first part and the second part. And then we solve and simplify. So if you notice, the red one only left one term, and for the black one I differentiate one with the purple color and one is the black color. Okay, the purple is for when exponential is equal to 0. Okay, and then the second one, the black one, is when exponential, the first part is minus tau over 2, but there are some cancellation and minus will be positive here, and the same goes for the second part. And when we simplify, the red one will be cancelled out, and so here we have only 4 terms left. And then we rearrange the equations as in the last line. Okay, if you look at equation, we notice that our equation can be rearranged so in form of cos theta, where we have cos theta equal exponential j theta plus exponential minus j theta over 2. So when we rearrange our equation, we have something like this: t over pi n squared tau minus t over pi n squared tau times exponential e j theta plus e minus j theta over 2, where our theta is n pi tau over capital T. By rearranging our equation, we have xn equal t over pi n squared times tau times 1 minus cos n pi tau over t. And we also know that 2 sine square theta over 2 equal 1 minus cos theta. So we try to substitute 1 minus cos n pi tau over t into sin square functions. And finally, we have xn coefficient as shown in the last equation. And this is actually a sin square function.